In this video, we're going to do the first example on this worksheet, double integrals in polar coordinates. So we're going to do question number 1 here. And question number 1 asks us to consider the double integral over the region D of x squared plus y squared dA, where D is the region given at right. So here is our region D. Question A asks us to set up the integral using rectangular coordinates. B says to set up the integral using polar coordinates, and C says to pick one of those two and actually evaluate. So let's start with part A. Part A, we can set this up as either a type 1 or a type 2 region. Let's set this up as type 1, which means that our x's are going to be within constants and our y's will go from boundary curves of x. Now the first thing that I see here is if we add a little bit of color to this region, we've got boundary curves here, one that I've drawn in red, the other one that I will draw in blue. And if we were to draw a delimitation between this region, we see that there is a distinct difference here. One place here we've got boundary curves on above and below of blue and red, whereas on the other side we've got blue and just the x-axis. So that means that we are going to need to split this up into two different integrals and sum those integrals together. So let's look at the first one. The first one, the x values go from 0 to, I've written over it here, but that says 1. So 0 is less than or equal to x is less than or equal to 1. And to figure out the y value, we're going to assume that this is a circular region here. And so that curve is going to be, in red, x squared plus y squared is equal to 1. And so we have y is the root of 1 minus x squared because we've got the top half of that circle. Same thing on the other side. If we go in blue, we've got the circle x squared plus y squared is equal to 2 squared, or 4. And so we're going to have y is the root, the positive root of 4 minus x squared. So in region 1, for any fixed x value, y is going to go from the red curve up to the blue curve. In other words, it's going to go from 1 minus x squared is less than or equal to y is less than or equal to the blue curve, which is the root of 4 minus x squared. So that gives me the boundaries of my integral, so double integral from 0 to 1 of the integral from the root of 1 minus x squared to the root of 4 minus x squared of our function, which is the root of x squared plus y squared. And I've done this in the order dy dx, but that's not all. We need to add to this the integral for the second region. And so the second region here, we're going to go from 1 to, that says 2. So in terms of the x inequality, 1 is less than or equal to x is less than or equal to 2. And now this time, for any fixed x value, the y value goes from the x-axis, which is the curve y is equal to 0. So that's less than or equal to y, which is less than or equal to the blue curve, which is still 4 minus x squared. So we've got the integral from 1 to 2 of the integral from 0 to the root of 4 minus x squared, and the function is still the same, x squared plus y squared, and this is still dy dx. So there is question A, although this really, it said the integral, it should really say the integrals. There are 2 that are necessary here. So we're going to go on to question B now. So now we're going to try and set up this region in terms of the polar coordinates. So let me redraw this region so that we can draw all of our lovely inequalities on it. So in terms of a polar region, we always want the inequality with respect to theta first. The inequality with respect to theta, theta is going from 0 to pi over 2. The inequality with respect to r, well, if we take this circle, right, this one was the one in red here to match above, that's the circle, r is 1. And then the circle in blue here, that's the circle, r is 2. So the inequality in terms of r is 1 is less than or equal to r is less than or equal to 2. So the inequalities give us our double integrals. We always put in polar coordinates theta on the outside. So 0 to pi over 2, the integral from 1 to 2. And then we have to change our function. Our function is here the square root of x squared plus y squared. And to convert that into polar coordinates, we're going to use the fact that r squared is equal to x squared plus y squared. And so that is going to give me the absolute value of r. But if we're taking r as a positive radius, and there's no reason that we can't, that just becomes r. So our function, the square root here gives us r, and then dx, or dy dx, dA gets replaced with r dr d theta. So if we write that by multiplying together those two r's, so the integral from 0 to pi over 2, the integral from 1 to 2 of r squared dr d theta. Okay, and then part C says pick one of the above and evaluate the integral. Well, I don't know about you, but I want to do the integral in B. It is much simpler. If you enjoy a challenge, knock yourselves out with part A, but I'm going to do part integral in B here. And so we can see that this integral, again, as in one of our previous examples here, this factors super nicely. That is constant with respect to theta, so I'm going to bring that out. The integral from 1 to 2 of r squared dr times the integral from 0 to pi over 2. That's not always going to happen so nicely that they will factor like that. In fact, we should see some examples where you have to absolutely go in terms of the iterated integral. But for now, we can take advantage of this nice fact. So 1/3 r cubed from 1 to 2 times theta from 0 to pi over 2, and then a little bit of subtraction here using the fundamental theorem. So 1/3 of 2 cubed, which is 8, minus 1/3 of 1 cubed, which is 1, times pi over 2 minus 0. So let's simplify our fractions here. 8/3 minus 1/3 is 7/3. So 7/3 times pi over 2 is going to give me a final answer for this double integral of 7 pi over 6.